Let's take a similar look at pass-to-pass accuracy. Pass-to-pass accuracy is often used in industry as a way to tout a better or more accurate piece of information, as well as to better represent the actual error that would be seen within the field by an ag vehicle on relative or subsequent passes. The standard metric to evaluate this is to require that passes be made within 15 minutes of each other. Typically, this pass-to-pass accuracy will yield somewhere between 2 and 3 times better accuracy than a traditional 24-hour static accuracy measurement. Now, most of the time these values are calculated not by actually running multiple or subsequent passes through the field, but rather they're typically calculated by collecting static data and then analyzing 15-minute segments of that static data in order to determine the worst case pass-to-pass accuracy scenario. So let's take a look at some pass-to-pass accuracy data, again provided by the John Deere website. The blue line again represents WAS, and you'll notice that there's a strong distribution of error associated with that WAS signal even over a short 15-minute time interval. As we add SF1 service, we approach the yellow line, which still has a fairly substantial movement or shift in overall GPS error, but is much less than the traditional or the original solution. SF2, or dual frequency correction, begins to approach the 4 centimeter accuracy level prescribed and provides a significant reduction in drift for these pass-to-pass applications. Now, if we have a solution here that provides, for example, 5 centimeters of pass-to-pass error, that'd be about 2 inches of pass-to-pass error. If we apply that to a field operation, then we would expect that our planter or tractor or sprayer would be able to pass within 2 inches of the ideal path each time it makes an additional swath through the field. The dynamic accuracy of the accuracy while moving is much harder to define and determine, but there is a standard that's currently under development that's helping address this. The key to dynamic accuracy measurement is that we're trying to evaluate how the receiver responds when it has to change direction quickly, track contours, make headland turns, or otherwise make quick changes in movement that aren't related to straight line guidance. This is very prevalent in parts of the U.S. where we have irregular fields or quite a bit of terrain in a farming operation. Here's a look at some data that was collected by the University of Kentucky back in the early 2000s with a couple different GPS receivers. Now, they took what's called a handheld, or an HH2, which is a handheld GPS receiver, as well as a precision ag receiver, and when they kept those stationary, which is denoted by the red dot, notice that the dark green, or the handheld GPS receiver, had a considerably larger area than the yellow dots, which are the precision ag receiver. What that tells you is in that static applications, when it's stationary, the precision ag receiver was able to provide much higher levels of overall accuracy. Now, look what happens when they took the same 2 receivers and they allowed those receivers to constantly travel along a curved path. And this was done by mounting the receivers to essentially a lever arm that was motorized and allowed to spin around at a fairly low rate of speed. Notice that both receivers had the general trend of following this circular path, but that the blue dots, which represent the handheld receiver, were actually much more closely coupled to the actual or desired path than the precision ag receiver was. This is the point behind using standardized metrics for position-based calculation. Once this was determined, the manufacturer was able to go back and adjust some of the software in the precision ag receiver to improve the overall performance. But without standards or the ability to go out and measure actual performance, we can't achieve these sorts of dedicated replicated comparisons of different GPS equipment. The University of Kentucky has further developed some of their GPS testing equipment to include a dedicated track that allows a GPS receiver to be exposed to multiple replicated field operations. Notice that we have two distinct long linear travel paths. Those allow for a direct measurement of pass-to-pass error. At the same time, there are some low-angled curves representative of contoured farming, as well as sharp angle, right angle turns, and headland passes. And the goal of this sort of test scenario is to evaluate that receiver's performance under a truly dynamic application, and an application that would be seen by many of the typical GPS receivers in use in agriculture. Here's an overall look at what that test track actually looks like down outside of the University of Kentucky's research farm, College of Ag Research Farm. As you can see, there's a small test device, GPS receiver, that can mount it on the track, and then self-powered as it translates along the entire line of the GPS track. So what's the data from this look like, or what do the results tell us about the performance of GPS receivers? On the left side of this image, you can see the pass-to-pass repeatable performance of GPS receivers traveling along the very linear straight line segments of that course. I don't have any units displayed, but you can certainly tell that those points are fairly closely coupled, and we would expect that over a 24-hour period, we might have anywhere from 8 to 10 inches of movement on a subscription-based system, and probably 1 to 2 feet of movement on a WASP-based correction service. What's more interesting, though, is to note the photo on the right, which details the GPS performance as it goes into and out of curved segments. And what this shows you is that the distribution in error along the straight line segments is very different than the distribution of error along the curved segments. So this GPS receiver is performing differently under a curved environment than it is under a straight line environment. Why is that important? Well, certainly if you're farming in an area that relies heavily on contoured farming or contoured applications, then it's important to get a good handle on how a GPS receiver would perform under those scenarios. That may not be of interest if you're farming square fields, but in much of the country, particularly in areas that have high agricultural populations, there's a good bit of land area that's covered by irregular shaped fields, or fields that are curved and contoured and aren't farmed in a truly linear path. So understanding this performance and variability is key to assessing which system will perform the best in this case. Now, the accuracy that's shown here is not driven only by the type of differential correction that's used. Oftentimes this accuracy is affected by the filtering that goes on in the GPS receiver to smooth overall response and performance. So while in a static application we would expect our RTK receiver to be much greater in performance than a WASP grade receiver, we may not see the same sort of trend when dealing with accuracy in dynamic applications, because this takes into more of account than just differential correction, but also that internal filtering and processing of the GPS signal. So it's not uncommon that a differentially corrected signal that has a higher rating of differential correction may not completely perform better under highly dynamic applications.